In this problem, we have a merry-go-round rotates at the rate of 0.5 radians per second with a 45 kilogram boy standing at a point 1.5 meters from the axis of rotation. What is the new angular velocity when the boy walks to a point 1 meter from the center? It says to assume that the merry-go-round is a solid 30 kilogram cylinder with a radius of 1.5 meters. We start, as always, with a picture. We're going to use a conservation of angular momentum in this problem. So we actually have kind of a before and an after picture. Then we'll write down our values, what we know in the beginning and what we know at the end. So in the beginning, we have this merry-go-round. It's a disc like you might see at just a park at the playground type area. And we have that the boy is standing at the edge 1.5 meters away. So I'll label that distance in my diagram. Then afterwards, he's going to walk to a point 1 meter, so he walks closer to the center. Now, the first thing we're going to write down is we're going to write down the initial angular speed. We're given here that it's rotating at a rate with an initial angular speed of 0.5 radians per second. We want to find what is the new angular velocity, the new angular speed, after he's walked to a point 1 meter away. Now we know some things about the values about the boy, and we know some values about the merry-go-round. And those values sometimes change. So I'm going to write what those values are in the beginning and what those values are at the end. And what we could possibly know are the mass and the radius. In the beginning, the boy has a mass of 45 kilograms. He is standing at a point 1.5 meters from the axis. So that's going to be the radius of the circle that he makes. It says that the merry-go-round is a solid 30 kilogram cylinder. And it says that it has a radius of 1.5 meters. Now, neither the mass of the boy nor the mass of the merry-go-round changes. The boy stays 45 kilograms, and the merry-go-round stays at 30 kilograms. However, in this new situation, the boy now has a radius of 1 meter based on the circle that he makes. But the merry-go-round doesn't change at all. The merry-go-round still has a radius of 1.5 meters. We're going to use this idea of conservation of angular momentum, which says that the moment of inertia times the angular velocity is equal to the angular momentum. So what we're going to have to do is we're going to have to use these masses and radii to solve for the moments of inertia. Let's start with the boy here in the beginning, the before. And then we'll look at the after. The boy is considered a point mass. A point mass is just kind of like a blob that moves around in a circle. It is not something that is actually revolving. It is or rotating. It is something that is revolving around a central point. And so, because of that, the moment of inertia is the mass times the radius squared. So, based on the shape and how it looks, we know our formulas for the moment of inertia. So this is of the boy. So therefore, we take the mass of 45 kilograms and multiply by the radius 1.5 squared. And that comes out to be 101.25 units or kilograms times meters squared. Then we look at the merry-go-round. And the merry-go-round, it says, is a solid 30 kilogram cylinder. And as such, it has a moment of inertia of 1/2 mr squared based on its shape. So we have 1/2 the mass, which is 30, times the radius 1/2, and only the 1/2 is squared. This gives us a value of 33.75 kilograms times meter squared. Now the boy, afterwards, still has the same shape, still a blob going around a circle of point mass, so still just mr squared. Mass is still 45, but now his radius is 1. And this gives us a moment of inertia of 45 kilograms times meter squared. Well, we notice here that the merry-go-round doesn't change at all. Has the same shape, same mass, same radius, and therefore the same moment of inertia of 33.75 kilograms times meter squared. Now we're using our idea of the conservation of angular momentum. And what the conservation of angular momentum says is it says that the angular momentum stays the same. And remember that the angular momentum is the moment of inertia times the angular velocity. So therefore, the moment of inertia times the angular velocity in the beginning is equal to the moment of inertia times the angular velocity at the end. But the question is, what moment of inertia are we talking about in these two parts? Well, the moment of inertia is the sum of the two that we just found. So these two together make the moment of inertia in the beginning. And these two together make the moment of inertia at the end. So now we go to our formula here, and let's rewrite that. The moment of inertia times the initial angular velocity equals the moment of inertia times the final angular velocity. Now I'm going to replace this moment of inertia with the two values that I have, 101.25, which is of the boy, and 33.75, which is the moment of inertia of the merry-go-round. We were also told that our initial angular velocity was 0.5. On the other side of the equation, again, the moment of inertia, we have the boy, which was 45, and we have the merry-go-round, which was 33.75. And we're trying to find that final angular velocity. So now if I solve here 101.25 plus 33.75, I get a value of 135. We still have times the 0.5. Over here I have the 45 plus the 33.75, which I get to be 78.75. And I still have my variable. From here I can multiply 135 times 0.5, and when I do so I get 67.5. And on this side I still have the 78.75 times my final angular velocity. Now to get my angular velocity I divide by the number connected to it. I divide by 78.75, since it is multiplied to it, We undo multiplication by dividing. And whatever you do to one side, you have to do to the other. On the right-hand side, they cancel out. To leave us only with the final angular velocity. And on the left-hand side, we divide to get 0.875. I'm sorry, 0.857. Now, of course, we need the units of angular velocity, or radians per second.